Special relativity is an idea proposed by Albert Einstein in 1905. Before this, we have Newtonian classical idea of absolute frame of reference, where the frame of reference can be fixed on an absolute point and absolute time. Special relativity regard frame of reference is to be relative to other frame of reference. Hence, space and time can be relative between reference points. The special in special relativity is that the idea only applies to initial frame of reference, i.e. non-accelerating frame of reference. The background of special relativity started from 1860, Maxwell's description of speed of light from his equation that described the nature of electromagnetic wave. The result of a speed of light being 3 times 10 to the power of 8, but he did not describe what speed of light is relative to. So Michelson and Morley measured the speed of light in different directions to investigate whether light traveled to what they call ether or not, which they found that the speed of light is the same in all directions and proved that the speed of light is the same in all reference and travel in constant speed. This led Einstein to propose the idea that there is no preferred or absolute reference point, and the speed of light is independent to its source and always stay at the speed of light. This led to several concepts that defy classical physics, such as time dilation, length contraction, and relativistic addition of velocity. First concept, time dilation. Einstein postulated in his imaginary experiment of an observer observing a light clicking on and off due to a light switch on a train, where the observer on the train will observe the light reflect vertically back to the switch, while an observer outside the train will see the light reflecting at an angle and travel longer distance. And as the light travels at a constant speed for both observers, the observer outside the train will perceive time it takes the switch to receive the light being longer than the observer inside the train. The formula are shown. The second concept is length contraction. Similar to time dilation, the perceived light coming from two ends of an object is different between the observer inside and outside the object itself, where the light moving in the line of object motion seems to reach the end of the object earlier, causing the object to appear contracted in the direction that it's moving. The third concept is the addition of velocity. As the speed of light is constant, regardless of its source or reference point, the light that are given off from a moving object stay at the speed of light, and so is the light coming off from the things that are thrown or shoot off that object, resulting in a less perceived velocity by the observer, as the light will reach the observer only at the speed of light, regardless of the velocity of the object. This concept can be better visualized by these lovely pictures of shooting a gun in a really fast moving box, where the velocity of the bullet are not just flat velocity of the bullet plus velocity of the box, but really slightly slower due to this relativistic effect. First question, how fast must a rocket travel to a distant planet so that an astronaut in a rocket aged 10 years, while the people back on Earth aged 100 years? As this question asks for a different time, we can immediately recognize that this is a time dilation problem. So we can write out our time dilation formula. Now that the question gives us the two times, so we need to find the velocity that produced those two different times. So now we need to rearrange so that v for the velocity is the subject of our formula. There's a little bit of tricks here that you can do if you're not sure which of the time you want to put as your main time or your dilated time. What you can do here is that you know that the ratio will always be a fraction of some kind that is less than 1. So that you can put 10 on the top and 100 at the bottom to produce this 0.1. Then we can do the algebra for the rest of the question and get the answer. Second question, You measure the length of a spaceship at rest relative to you to be 500 meters. How long will an observer measure it to be, even if the observer flies past a spaceship at 0.75 c? This question gives you a velocity and a length and asks for different lengths. You can immediately recognize that this is a length contraction question. So you can write down the length contraction formula. This question is quite straightforward, as it already gave you the resting length and the velocity of the observer. So you can just plot the number into the formula and work into relativistic length straight away. And that's the end of the question segment. Before I end this video, I'd like to give you some parting thought on relativity. In this video, the matter of special relativity might seem a bit far too detached from the real world, with things needed to move really fast or for it to have any effect but special relativity has its use. In our society, we happen to rely on one major technology that features fast moving things, the GPS or Global Positioning System, where we use signal from satellite to find out where we are on Earth. These satellites are moving really fast, in order of 2 to 10,000 meters per second. And if there's no adjustment for spatial relativity, the time and length difference caused by time dilation and length contraction will render all GPS devices useless. So we need spatial relativity to keep our GPS in check. So remember, even something so bizarre like time dilation and length contraction, there's still real phenomenon that will affect our technology and our life.